Our topic today is elastic potential energy. So think about this picture, Katniss Everdeen in the Hunger Games, and how this relates to elastic potential energy. So can a Nerf dart gun cause a change in anything? Well, yes, right? It could knock a can off a counter. It could hit somebody too. So does a Nerf dart gun have energy? Yes, because it can cause change. Remember, anything that can cause change has energy, and it can also do some work, right? So what kind of energy do you think it was or it has? So it is elastic potential energy. So let's explore this a little bit. So the compressed springs of a dart gun store elastic potential energy. So as you're pulling the trigger, when the trigger is pulled, the springs apply a force to do work on the dart, and that causes a movement. So elastic potential energy is energy stored in elastic materials. As a result of stretching or compressing. So things like springs, rubber bands, or like in the picture um, with the bow and arrow, that is also elastic potential energy. So the amount of elastic potential energy stored is related to the amount of stretch of the device. So the more stretch, the more stored energy. So sometimes when you see people with bow and arrow, you see them stretch it out really far, and they have to use a lot of energy to pull that bow back. And as soon as they let it go, they're releasing that energy. Compressing a spring creates potential energy. So you're compressing it because you have to do work against the force of the spring. So the spring wants to move back to its original position, but when you compress it, you're bringing it together, and you have to do some type of work in order to keep it compressed. So a compressed or stretched spring stores potential energy as long as you're doing that, compressing or stretching. So we can calculate the elastic potential energy of a spring if you know the distance it is compressed or stretched. And we also have a spring's constant. This spring constant is a rate in which the change of force it exerts is divided by its change in displacement. And all it is a constant, and it's a given value. So the formula for elastic potential energy is shown here. So sometimes it'll be shown as a capital E and lowercase p, or we'll just say EPE, elastic potential energy, equals 1/2 K, and K is our spring constant that is always given. X is the extension of the spring given in meters, okay, squared. So the elastic potential energy of a spring is directly related to the square of the distance, right? We're squaring distance, whether it's compressed or stretched. This means that it can increase or decrease exponentially, resulting in a curved graph. So a spring with constant K equals 450 newtons per meter. So this stays the same within this problem. It is compressed by 0.13 meters. So this is our X value here. So that's how much we're moving. How much energy is stored? So because this is a spring, we know that it's an elastic potential energy problem. So once we have our variables here on the left, we can use our elastic potential energy formula. So 1/2 times K, which is given as 450, times 0.13 squared, gives us an energy, elastic potential energy of 3.8 joules.